Today we are gonna start a new topic on knowledge graphs. So far, our focus was on trying to learn node level tasks, basically node level embeddings, graph level embeddings, and use them for different tasks such as node classification and node basically graph level regression and classification problems. So far we haven't looked at any type of link prediction problems, and today we're gonna start doing that. So what are knowledge graphs? Let's say that we have a set of information. We can usually write down the set of information that we have using different basically entities that are included in that information and the relationships between these basically entities. So we usually represent this. I will give an example after this abstract definition. So we will usually define these using a triple starting from a subject, a predicate, and an object. So subject and object are two entities that we have, and predicate shows how these two are related to each other. Now, so if we have basically some information, some knowledge about something, we can represent all this knowledge using a set of these triples. So let's basically look at this statement. The statement says Matthew Perry is an actor who portrayed the character Chandler Bing in the television sitcom Friends. Now, it is some information. It includes some entities and some relations between these. Right, so now we can write this down using these triples. So first we have Matthew Perry, which says that is an actor. So we have Matthew Perry. Relation with actor is profession. So there are two entities, Matthew Perry and actor, and these are connected using a relation, profession. Then we have another one. We say that Matthew Perry starred in Friends. So we have Matthew Perry is related to Friends with basically a relationship starred in. Then we have another triple, which says Matthew Perry portrayed Chandler Bing, right? So again, Chandler Bing, one entity, Matthew Perry, another entity, and these are related together using the relation portrayed. Then we have Chandler Bing in the television sitcom Friends. So it means that this is a character in that TV show. So Chandler Bing is related to entity Friends with the relation character N. And lastly, we have, for instance, we're saying that the television sitcom Friends, so it is saying that the genre for sitcom, for Friends is sitcom. So it is relating to these, basically these two entities, Friends and sitcom, using the essentially edge relation, using the relation genre. Okay, so far so good. We have only looked at these basically as a statement as a set of triples, right? We haven't constructed any graphs or anything like that. So we just have a set of triples and that's it. Now, we can use graphs, definition of graphs, to combine all these triples together and represent them instead of a set of triples on a graph structure. So in this basically representation, what we do is that we represent entities with nodes and we represent the relation between these entities using edges. So something like this. So the first one, the subject basically entity, is represented by the head node. We show that with VH. And then VT is the tail node, which is representing the second basically which is representing the basically second entity, the object. Now, so each of these triples that we are dealing with in this set is representing some fact in the knowledge that we have, in the information that we have. Now, when we represent all these facts on a graph structure data using basically this type of representation, we construct a graph which we call a knowledge graph. So a knowledge graph is essentially representing some factual information, some knowledge that we have about some matter, about some basically about the world, about some medicine, about something, right? So in the previous example, for instance, we can represent the set of triples that we have using this type of graphs. So we have entities like actor, Matthew Perry, we have friends, we have sitcom, and we have Chandler Bing. These entities are represented with nodes in our graph, and then we have edges that are representing relations between these entities. So we have genre, which connects friends with sitcom. We have starting, which basically connects Matthew Perry with friends, and so on and so forth. Now you can see that previously we had multiple triples that included Matthew Perry. Now we only basically use Matthew Perry as to represent basically this entity using a node, and then we can have multiple relations between this Matthew Perry entity and other entities on the graph. So now you can see that these nodes, these entities have different types, right? So this is a person, this is a profession, this is a TV show, this is a genre, this is a character, right? So they're not of the same type, right? So on this knowledge graph, we will, and similarly, we have relations that are all different from each other. We have this relation called genre, we have this relation character in, start, in, portray. So these are all edges of different types. And then we have nodes of different types as well. So this is not a human, this is a human. This is basically not a human again. So the types of these nodes are different from each other. Therefore, a graph with different types of nodes, different types of edges is a heterogeneous graph. So just quickly, let's review what this means. A heterogeneous graph is a graph that is constructed of nodes and edges of different types. In this graph, we represent each edge using a triple, U, tau, V, where U and V are the basically two ends of our edge, and tau is the type of that basically connection, type of that relation, type of that edge. So also nodes are from different types. So we basically take all the nodes in our graph and we divide these into disjoint subsets. So we take all the nodes that we have, we divide these into disjoint subsets, bless you, a union of which is going to be the whole set of all the nodes that we have, and these are non-overlapping subsets. So now, in many scenarios, we have types of edges that are restricted between two different types of nodes. So, for instance, we have genre, which usually connects a TV series and some basically genre that it has, right? So it doesn't connect, for example, a person to a character, right? So this type of edge is only between two different, basically two specific type of nodes. So let's say that genre can be between sitcom and, for instance, How I Met Your Mother. So let's basically look at a quick example for polypharmacy side effect graphs, where we have two types of nodes and three types of edges. we have some edges for just to be clear, I have so that it's more clear, I have represented different types of nodes with different basically shapes, but it doesn't mean anything other than these are different types. So we have here squares, which are representing drugs. We have circles, which are representing proteins. And this graph is showing how basically these are interacting with each other, different drugs and different proteins. So when we say that, so we can have three types of different relations between these, interactions between these. We can have drug-drug interaction, meaning that these two drugs, if you take them together, they will have side effects. So edges between nodes in V1 are representing side effects, for instance. These are proteins. If a drug is connected to a protein, this edge type is showing that the drug is targeting that protein. So it is a drug-protein interaction. And then we have a protein-protein interaction, meaning that these two work together, these two proteins work together to basically in some metabolism in your body. So this is just one example of a heterogeneous graph. We have different types of nodes, different types of edges, and different types of edges can be only between a particular subset of the nodes. So for instance, you can have drug-drug interaction between protein and drug, right? So now back to our knowledge graph discussion. Knowledge graphs, so the term knowledge graph has been around since maybe 2010 that Google presented its knowledge graph. In the recent decade, there have been many knowledge graphs created, and let's go over some examples of these. For example, we have Wikipedia, which is constructed from information boxes in Wikipedia. So it basically gathers information from automatically or in whatever manner. It goes and creates, basically gathers all information from these info boxes and represents it as a graph. Then we have Freebase, which is basically the goal for Freebase was to gather all the knowledge that we have. So human contributors tried to construct this large graph, but then Google purchased this in 2011, I think, and it made it the base of its knowledge graph. We have in commerce, we have different knowledge graphs. Amazon has its own knowledge graph where it tries to use that to connect basically people, different products, different basically factories, for instance, different sellers, and so on and so forth. Uber has its own basically knowledge graph that it uses for its Uber Eats platform to connect people with foods and basically tries to make suggestions for different restaurants, different foods that you might want to try when you're not sure what you want. So Airbnb has the same thing. It basically tries to connect people, accommodations, different rentals, and so on, and basically different some experiences that you can basically book on Airbnb. On finance, there are different companies that have constructed their own knowledge graph. For instance, Bloomberg and Capital One, which do some basically risk assessment analysis and some financial analysis. And there are more of these. There is Capital One, there is Wells Fargo, there is Banca d'Italia, and so on and so forth. On social media, there's LinkedIn, there's Facebook. LinkedIn is trying to connect people with jobs and basically people who hire. So employees, employers try to essentially link you with a good job, for instance. AstraZeneca is another one, which is essentially a knowledge graph of genomic research. People are using this, for instance, to do more, basically some research on these.
So I'm not sure about this particular one, but for instance, you can learn these graphs in order to be able to predict what type of drug can potentially be of use for a particular disease, for instance. Very much like, finding the missing link between a protein and a particular molecule. Web searches now are very much using these. Previously, we were using, we were essentially using PageRank type of algorithms in order to rank different websites based off of some score. Now they're basically their centrality score. Now we can use this Google Knowledge Graph in order to answer these search results in a better manner. And especially they're being used to construct these info boxes here. So for instance, I search my name and it is representing like 5 different people, the 5 different entities that might be of interest for the person who is searching these. So people also search for these as well. So these Microsoft Bing thinks that these people are connected to me, and 2 of them I don't know. So so it's not that it's always accurate, but based upon the data that it has, it thinks that these are connected to me. And this has basically different entities about me. It has where studied, or where works, or so on and so forth. So for different people, when you search that, it tries to represent these different, relations, these different entities using these info boxes. Or for instance, when you search, for instance, movies of 2019, you usually get a set of movies here, which is again using the structure of the knowledge graph. And many of these digital assistances like Siri and Alexa and Google Assistant, these are also using knowledge graphs in order to represent whatever answers that they give to you. All right, so very beautiful. Now, what can we do? What can we do to improve these knowledge graphs? So that's one question that we want to answer today. Knowledge graphs are essentially gathered from the knowledge that we have on web, for instance, or on some book or some database. So these are not always complete. For instance, Freebase have for a lot of people, a lot of entities on it. And for 71% of these people that are on Freebase, we don't have the entity place of birth. So we don't know where these people were born, right? So the idea now is that this is incomplete. And if we construct a knowledge graph, the links are missing here. There are some cities that are represented on that knowledge graph. There are some people that are represented on that knowledge graph, but these are not connected with each other. So we want to find these missing links. And that's this task, we call that knowledge graph completion. So using that, we can, number one, complete this knowledge that we have. For instance, the knowledge about where someone was born. Someone knows it, but we don't have it there. So it's finding the missing data. And the second one is predicting new facts, right? So let's say that we have a drug discovery graph, and we want to see what new drug can be related to what new protein. Now, in this graph, no one knows which one is useful. So we are essentially trying to predict a new fact about the world using this knowledge graph. So in general, the knowledge graph completion, the problems that we deal with are link prediction. Although in some cases, we can encounter node classification problems as well. So let's say we only looked at a part of this knowledge graph about some basically actor and its relation to different entities. Now let's say that we have more information. We also know about the TV series, How I Met Your Mother, and we have added some information from that as well. So we know, for instance, this person, Josh Radnor, plays in this movie. Then we know that this is also an actor. We know that it portrayed Ted Mosby, but we don't know what's the relation between this entity, Ted, and this entity, How I Met Your Mother, right? So based off of this graph, we can learn how to represent this relation character in, and then we can learn embeddings for every node here, and then we can use that in order to predict what's the relation between Ted and How I Met Your Mother, which is character N. So finding this missing relation between two different entities is part of our link prediction problem. So in order to solve our graph different levels of graph tasks, so far we have tried to learn embeddings, learn feature vectors that represent that data on different levels, right? So we have had node classification problems where we learned node embeddings, and we used those node embeddings to plug that into some machine learning approach in order to classify or in order to regress some or predict some value for some molecular graph. Now here, we're gonna do the same. We're gonna learn some entity embeddings. So the whole thing is called knowledge graph embedding, and it's constructed of entity embeddings, which we are representing like ZH or ZT, like we were representing for node embeddings. But we also here have a relational embedding as well. So we are learning node embeddings in conjunction with relational embeddings that we are here representing with vector R tau. So R tau is representing the embedding for relation type tau. So now there are different methods, there are different models to learn these these knowledge graph embeddings. But for all of them, but basically we need to assess them. We need to assess if they're capable of representing, learning, and inferring different relational patterns. So we will look at some basically logical patterns that we will encounter in relations that we usually have here. So number one is symmetric relations. So in symmetric relations, we say that if node 1 is related with node 2 with some relation tau, that means that basically the other one is related to the first one using the same relation type as well. So that means in the graph terms, if VH is connected to VT using node H type tau, then VT is also connected to VH using H type tau. And note that these are directed edges. So for instance, when we say Bill is married to Hillary, that means that Hillary is married to Bill as well, right? So if we have a model, it should be able to learn embeddings for the nodes, for the edges, such that we can use those embeddings, and from one, we can predict the other one. So the second example is anti-symmetry. So for instance, VH is related to VT using some H type tau, then that means that VT is not connected to VH using that same H type. So if someone is your advisor, you can't be the advisor of your advisor, right? So if someone is your father, you can't be basically connected to that entity using relation type father, right? So only one can be related using this edge type to the other one, not both way around. So that's called anti-symmetry. We have inverse. In inverse, when we say that VH is connected to VT using edge type tau1, that will mean that node VT is connected to VH using another type of relation tau2. So for instance, we can say Jesus is child of Mary. That will indicate that Mary is parent to Jesus, right? So it's parent of Jesus, right? So knowing that Jesus is a child of Mary will convey that Mary is parent of Jesus, right? So edge type, these two entities having type child of between entity one and entity two means that we have tau2 between entity two and entity one. So last relational pattern that we want to look at is compositionality. In this essentially logical pattern, we say that if node 1 is connected to node 2 using type 1, and node 2 is connected to basically node 3 using type 2, we would infer that node 1 is connected to node 3 using a new type 3. So let's give an example for this. Let's say that in college, usually we have, football teams, varsity teams, they draft students from whoever that is studying there, right? So our football team is not gonna take students from UCLA, right? These are all Notre Dame students that they're taking. So if I have two edges here, for instance, I have Ian Book drafted by Fighting Irish, right? So Ian Book plays for Fighting Irish. And then I have Fighting Irish is related to Notre Dame by Edge School, right? Fighting Irish is the football varsity team for Notre Dame. Now, from these two statements, I conclude that Ian Book is enrolled at Notre Dame. So that means that I have node 1 with node 2, type 1, node 2 with node 3, type 2. I will conclude that node 1 is connected to node 3 with a third type of relation, and that's called compositionality. Now, if we want to basically come up with some model who is learning node embeddings and edge and basically knowledge graph embeddings, we want these embeddings to be able to represent these logical patterns. And that's what we use to assess different models that are proposed. Now, before going there, what are we going to use in order to learn these? You're gonna use the same type of basically shallow embeddings that we used before to learn node embeddings. Now, in principle, we can use graph neural networks, right? But just for the simplicity, in order to focus on the model that is learning the essentially the decoder part of our work, you're gonna only use a shallow embedding, which means that we don't have a encoder, it is just some dictionary lookup. Now, in the embedding, and the basically shallow embedding approaches, we said that we have 4 things that we want to learn. Basically, we want to deal with. We have so in the shallow embedding, all right. So in the encoder-decoder architecture, there are 4 things that we deal with. We deal with encoders, we deal with decoders, we deal with a loss function, and then we deal with some similarity measure that we want to reconstruct using our decoder. When we say we use a shallow embedding, it means that we are using an encoder that is just a dictionary lookup. So we are directly learning the embeddings in our optimization process. And here we're going to only focus today on the decoder, the type of decoder that we're dealing with. So when we were learning node embeddings using our shallow embedding approach, we had multiple similarity measures that we wanted to reconstruct, right? We took any similarity measure that we looked at the beginning of the semester, and any type of node similarity measure, and we were able to reconstruct those in order to basically learn the node embeddings in the process. However, here we don't really go there because our relations are more complex, because we have not only one edge, we have different types of edges. So it will get nastier if we basically try to learn higher level similarity measures. So in our essentially knowledge graph embedding approaches, we only try to reconstruct the existence of the edge, and that's it. We're not going to go further than that. So that means that given two nodes, Vi and Vj, we want to reconstruct the relationship between these two. So again, we said that we have different edge types in our graph, and that essentially causes some issues when we try to learn. Basically, we want to reconstruct the relationship between the different nodes. So what we want to reconstruct is called a multi-relational neighborhood. And in order to do that, we need to learn embeddings specific to different types of edges that we deal with. So our decoder this time, if you remember our node embedding decoders, we're taking two node embedding Ci and Zj. Now, in it, and they were returning some basically score, some likelihood value, right? Now we also, in addition to those two, we also have some edge embedding. So essentially, we have a set of different types of edges. So our decoder takes that as input as well. Now we have node Vi represented by embedding Ci. We have node Vj represented by embedding Zj, and we have edge type tau represented by our tau. And our decoder takes these and returns some basically value, which says that how likely is that we have an edge of type tau between these two nodes, Vi and Vj. How plausible is it that this edge exists between these two nodes?